Welcome to Chapter 17, Thermodynamics Revisited, Screencast number 1. This is for Chem 1B at Shasta College. Let's begin by remembering some ideas from Chem 1A, starting with the first law of thermodynamics, which states that in any process, the total energy of a system and its surroundings is constant. Note that this is also known as the law of conservation of energy. So if we have a system, which could be as simple as, say, a flask of water. It could be a bunch of chemicals or compounds that are reacting with each other. The system is going to be whatever we're interested in, substances or a process or reaction that's taking place. And when we have a system, its energy can change if energy either flows into the system or out of the system from its surroundings. And we can always track these energy changes, and they can occur either via heat or work, Q and W respectively. And if heat flows into or out of the system, that'll change the energy of the system. If work is done either by or on the system, that'll change the energy of the system. But no energy disappears, no energy appears out of thin air. We can always track that if the system absorbs 200 joules of energy from the surroundings, then the system's energy goes up by 200 joules, and energy overall hasn't changed. It's constant, it's conserved. Now remember that there's also a second law of thermodynamics, which states that in any spontaneous process, the total entropy of a system and its surroundings always increases. Also remember that entropy can be thought of in several different ways. We have started by thinking of entropy kind of loosely as a measure of disorder of something. And so the total disorder of a system and its surroundings always goes up when processes occur. So you always start with things that are more ordered and end up with a situation where there's more disorder in the world. Now, we can follow this in a little more detail by looking at one of the ways we define entropy, which is as a ratio of heat, Q, to temperature, T. So delta S is heat flow in or out of something, a system or surroundings, divided by temperature of that something. And note, of course, the temperature has to be in Kelvin. So let's take a look at this via an example of a system that we're here representing just by a blue cylinder. It could be, again, a beaker of water or some chemicals that are reacting. It's the things we're interested in, the process we're interested in. And the system will have a delta H, an enthalpy change, and a delta S, an entropy change. And we put a little subscript cis on each of these to clarify we're talking about the system. Now, suppose we talk about or deal with a system that undergoes an exothermic process, so it gives off heat. Well, the heat, or Q, of the system is equal to the delta H of the system if the pressure is constant, which is often the case for us. And if the system gives off energy, then the surroundings absorb that energy. And in general, the delta H of the surroundings is equal to, but opposite in sign to, the delta H of the system. So if the system gives off 2,000 joules, then the surroundings absorb 2,000 joules. Note that this relationship holds whether we are talking about an exothermic process or not. If it's an endothermic process, the relationship's still true. It's just that the delta H of the system would be positive and the delta H of the surroundings would be negative. So if we track the delta S of the surroundings, which is equal to Q over T for the surroundings, which is equal to delta H over T for the surroundings, and that is equal to negative delta H for the system over T. So we've transformed our delta S for surroundings in terms of other quantities, delta H and T, for the system. So if we now look at the statement of the second law of thermodynamics, that the entropy change total is equal to the entropy change of the system plus the entropy change of the surroundings, recall that that's a positive number. The total entropy always goes up, or the delta S total is always positive. And then remember also that we now have a different relationship that could be used to replace delta S of the surroundings, which is also equal to negative delta H of the system over T. And we now have a relationship only in terms of thermodynamic quantities of the system. Delta S system plus negative delta H system over T is always greater than 0. If we look at this specifically with a known example, the combustion of propane, C3H8, that is a process that gives off a lot of energy. Delta H is negative 2,219 kilojoules, but that also decreases disorder because gas reacts to make gas and liquid, and this process has a negative delta S. So if we track entropy change of the surroundings, that's going to equal negative delta H of the system over T, which is going to equal negative 2,219 kilojoules over 298.2 Kelvin if we're doing this reaction at 25 degrees Celsius. And that works out to be 7.441 kilojoules per Kelvin. And we often convert that to joules per Kelvin because we often deal with entropy changes in terms of joules per Kelvin rather than kilojoules per Kelvin. Both are perfectly fine. And if we now look at the total entropy change for the world, it's equal to the delta S of the system plus the delta S of the surroundings. Delta S of the system was negative 375 joules per Kelvin. Delta S of the surroundings, we just calculated to be 7,441 joules per Kelvin, which gives us a total delta S of 7,066 joules per Kelvin. And it's a positive number, which of course it has to be for a spontaneous process, and it's really big. So this is a very spontaneous process. And in general, what we can do is essentially the argument that we just went through, looking at the total entropy change of the universe in terms of the entropy change of the system and surroundings as always being greater than 0 for a spontaneous process. And if we then take this equation that we just developed, delta S system plus negative delta H system over T is greater than 0, and then do a little bit of rearranging. In other words, let's first multiply both sides by T, which gives us T delta S of system minus delta H of system is greater than 0, and then multiply everything by negative 1, and then reversing the order of the two terms, delta H and T delta S. And that, delta H minus T delta S, is what we now refer to as delta G, the Gibbs free energy change, and that is less than 0 because the sign of the inequality reverses as we after we multiply by negative 1. So this is what Gibbs actually recognized, is that we can look at one quantity called G or delta G that describes what's going on thermochemically, and it's a composite of the enthalpy changes delta H, the entropy changes delta S, and the temperature that the system is at. So let's do one more example. Under what conditions is the decomposition reaction of calcium carbonate, CaCO3, spontaneous? So calcium carbonate decomposes by making calcium oxide and CO2 gas. Its delta H is 177.8 kilojoules. Its delta S is 160.5 joules per Kelvin. And if we calculate the Gibbs free energy change, delta G, from delta H minus T delta S, and note that if delta G is negative, then we have a spontaneous process. If delta G is positive, we have a not spontaneous process. Therefore, if delta G is 0, that's where the process goes from or changes from being spontaneous to not spontaneous. And what that gives us is delta H minus T delta S is equal to 0. And solving that for T, we get delta H over delta S, which equals 177.8 kilojoules over 0.1605 kilojoules per Kelvin. So here I chose to convert the delta S into kilojoules per Kelvin rather than changing the delta H into joules, because we want our units to agree so that in this case they'll be able to cancel. And this gives us 1108 Kelvin, which of course is the same as 835 degrees Celsius. So at 835 degrees Celsius or so, the decomposition of calcium carbonate goes from spontaneous to not spontaneous, or not spontaneous to spontaneous, depending on whether the temperature is increasing or decreasing. Okay, now what does it mean for the temperature of 835 degrees Celsius to be where the reaction goes from spontaneous to not spontaneous? Well, here's the reaction. And note that the equilibrium constant for this reaction is simply the pressure of CO2 gas, because calcium carbonate and calcium oxide are both solids. And if we graph carbon dioxide pressure versus temperature, you might want to think about what the graph might look like. And it looks like this. Very little, essentially zero, carbon dioxide at low temperatures. As we start getting near 835 degrees Celsius, the pressure of carbon dioxide at equilibrium increases. By 835 degrees Celsius, the pressure of carbon dioxide is 1. And then after that, as we go to higher and higher temperatures, the pressure of carbon dioxide increases more and more and more. So above 835 degrees Celsius, we have a spontaneous or product-favored process. Below that, we have a not spontaneous, not product-favored, or reactant-favored, if you will, process. And notice it's not like the system hits at 835 degrees and poof, all of a sudden the reaction takes place. It's just it gradually becomes more and more product-favored. It goes through sort of a nice balance at 835 degrees Celsius of 1 atmosphere, and then, so K is equal to 1, and then as the temperature rises, the reaction gets more and more and more product favored, or more and more spontaneous. We should probably mention the general conditions for spontaneity, and remember, of course, delta H minus T delta S is equal to delta G. And if we consider the possibilities, delta H is negative, delta S is positive, that will give us a delta G that's definitely negative, and that means our process is spontaneous for sure, definitely. If we have a positive delta H, a negative delta S, then delta G is definitely going to be positive, and the process is definitely not spontaneous. But if delta H and delta S are both positive, or if delta H and delta S are both negative, whether a process is spontaneous is going to depend upon temperature. And if you look at the equation and think about what would happen when your temperature gets higher or lower, you can conclude that the delta G value will be negative if the temperature is high enough, if we have positive delta H and delta S. And if we have negative delta H and delta S, then the delta G could be positive or negative, but if the temperature is low enough, we'll get a negative delta G and therefore a spontaneous process. Now, one more set of things to talk about before this screencast is over, and that is the meaning of Gibbs free energy and change in Gibbs free energy. And there are 3 ways we can look at this. One is the standard Gibbs free energy of formation, delta G of formation, or delta G sub F, is the reaction free energy for forming the compound from its elements in their most stable form under standard conditions. Here are some compounds with their associated Gibbs free energies of formation, and the ones that have negative Gibbs free energy of formation, the ones that have negative delta Gs, those are compounds that are thermodynamically stable relative to their elements. So, for example, water has a delta G of formation of negative 237 kilojoules per mole. That means when water forms from H2 and O2, its constituent elements, 237 kilojoules of energy is given off in a sense, and that makes the product much more stable than the things that made it up. Conversely, things like benzene that have a delta G of formation that's positive. So C6H6 is benzene. It has a delta G of formation of 124 kilojoules per mole. That is thermodynamically unstable relative to its elements, because to make benzene, you'd start with carbon and hydrogen, and you'd have to add 124 kilojoules of energy to make that product, so it's not stable relative to its elements. And then, of course, anything that has a delta G of formation that's 0 is equally stable to the things it was made from. And since delta G's of formation are making the substance from its constituent elements, that means that our starting point is that the delta G of formation of any element in its most stable form is 0. The second way to look at Gibbs free energy or Gibbs free energy change is that it's the maximum amount of energy that's available, or we could say free, to do work. So note here that free is kind of a bad term to use for Gibbs free energy. It maybe should be better stated, or would be more appropriately stated, as Gibbs available energy, because when a reaction takes place, like the gummy bear combustion that you saw in class, this process has a delta G of negative 6,700 kilojoules for 1 mole of sugar reacting with 8 moles of potassium chlorate to make the product as shown in the reaction. What this means is 6,700 kilojoules of energy are available to do some useful work. So when this reaction takes place, some of the energy given off in the form of heat is given off as heat, but it's not, we can't harness it, we can't do anything useful with it. So the Gibbs free energy, another way to look at it is it tells you for a given process how much energy from that process is free or available to do work. And then third, delta G is the criterion for spontaneity, and at constant temperature and pressure, the direction of spontaneous change is such that the delta G is negative, which means that G itself decreases. And if we have a generic reactants makes products kind of reaction, it has a free energy graph that looks something like this. If we graph free energy versus course of reaction, where on the far left we have reactants, fully 100% reactants, and on the far right 100% products, then the Gibbs free energy of the reactants is some value, and the Gibbs free energy of the product is some other value, and here it's lower than that of the reactants. And then the equilibrium position is somewhere in between reactants and products, and we can think of this as sort of an analogy of a ball rolling down a hill or a rock rolling down a hill, whereas here is where we start, here is where we end, and the equilibrium position is somewhere in between, and it's going to be at the lowest spot of energy, or of free energy. So here are some a little more precise examples. We have a Gibbs free energy curve for the reaction from reactants to products here, and note that the position of equilibrium is the low point of Gibbs free energy. That's where delta G is 0 and where G is a minimum. So those of you who are familiar with derivatives and tangents, here we have a tangent line that is has a slope of 0, and this is the low point on our curve. And in a closed system, reaction's going to continue until equilibrium is reached, those good old equilibrium ideas we've seen before. But now we're coupling this with what happens in terms of free energy, which is that it decreases until the minimum energy of G is reached. So if we start here with quote-unquote reactants, Gibbs free energy decreases until equilibrium is reached. If we start with pure quote-unquote products, Gibbs free energy decreases until it reaches equilibrium, and that is the minimum G value and the low point on our curve. And this is going to occur whether the reaction is product favored, which has a negative delta G, or reactant favored, which has a positive delta G. So a product favored reaction is going to have a curve that looks something like this, where the equilibrium position is much farther towards the product side. A reactant favored process will look more like this, where Gibbs free energy goes up and the equilibrium position lays closer to the reactant side. That's it for screencast number 1.